Getting straight information about the Higgs boson can be hard work. When Time magazine nominated the Higgs boson their Person of the Year, each sentence in the nomination paragraph contained serious factual errors. Some of these are errors I've been guilty of, as well, such as calling physicist Peter Higgs a Scottish physicist, even though he was born in England, not Scotland. Sorry for that slip, Dr. Higgs. But even in more meaningful ways, the science related to the Higgs boson can be confusing. For example, it's common to say that the Higgs boson is what gives particles mass, but this claim is misleading in many ways. For one thing, it's really the Higgs field that gives the mass, through a process called the Higgs mechanism. The Higgs boson itself is a rare manifestation of this field as a particle, which only shows up and can be detected when a lot of energy is pumped into the field, such as in the Large Hadron Collider LHC. And the Higgs isn't even needed to explain all of the mass, or even most of the mass, in our universe. Quarks and the particles made up from them, protons and neutrons, for example, all have mass even without incorporating the Higgs mechanism. The masses explained by the Higgs mechanism are the relatively small amount of mass possessed by the W boson and Z boson. The basic or garden variety Higgs boson completes the standard model of particle physics by explaining where these masses come from, and evidence released this week has made it clear that the particle announced last summer by researchers at CERN probably fits the bill. But many theoretical physicists had been hoping for a bit more, because if the LHC had discovered multiple versions of the Higgs boson, it would have provided evidence that would have supported the theoretical physics concept of supersymmetry. This week's announcement, which includes analysis of about 2.5 times more data than what was available last summer, gives no clear evidence of supersymmetry. For a while now, there has been talk within the physics community about the need to look for new ideas. The more standard than hoped Higgs leaves scientists in the position of having to really consider abandoning the notions at the heart of supersymmetry, which has been a cornerstone of theoretical physics model beyond the standard model for over a quarter century. The failure to actually demonstrate supersymmetry is a serious problem, as suggested in Lee Smolens's 2007 book The Trouble with Physics, but has more recently been taken up by other physicists who are considering what could take supersymmetry's place if the evidence found at the Large Hadron Collider doesn't fit with that model. Young physicists have to really consider whether they want to continue investigating supersymmetry or begin trying to find whole new directions to answer the outstanding great problems in theoretical physics. More results may be well in coming. The Large Hadron Collider has shut down for a couple of years, set to go back online in 2015. At that point, it'll come back online with enhancements to its power and, potentially, any Higgs results that would extend beyond the garden variety Higgs might show up at that time, although proving conclusively that this is the Higgs boson will take a few years' worth of data collection. Even with the data that exists, though, new areas of research are coming to light. Plugging the existing data into the laws of physics as we understand them resulted in a result, announced by a Fermilab scientist last month, that our universe might be unstable. If these results are true, our universe will still have billions of years, but then will be wiped out as it decays into a more stable alternate universe.